In the heart of Amazon rainforest, an elder of an isolated tribe walks through the familiar paths of his village. Every tree, every animal, every sound of the forest is as known to him as his own heartbeat. He moves with purpose, his feet barely making a sound on the soft land as he gathers herbs. The jungle, with its towering trees and vibrant wildlife, is his entire world. He knows no place beyond its lush canopy. One evening, as the tribe gathers around the fire to share stories and meals, a strange noise breaks the usual sounds of the forest. The elder looks up in the confusion. The sound grows louder, and soon the source of the disturbance becomes visible. A metal bird, larger than any creature in the jungle, comes down from the sky. It lands in a clearing nearby, its wings unmoving and its body shining under the setting sun. The tribe is both scared and curious. They watch from the safety of the trees, whispering among themselves. The elder, brave and wise, approaches the strange bird with his heart beating every second. He is greeted by beings unlike any he has seen before and speaks in an unfamiliar tongue. They offer gifts and try to communicate, but the elder's first instinct is to protect his people. He gestures for the tribe to retreat, keeping a watchful eye on the newcomers. As the sun sets and the metal bird departs, the elder stands at the edge of the clearing, watching the sky darken. He wonders about the world beyond the jungle. Where did these visitors come from? What lies beyond the vast canopy that the bird has always known? The elder's universe, once limited to the boundaries of the forest, now feels smaller and wonders about other worlds and unseen wonders. The observable universe is an immense structure filled with various celestial objects scattered across vast expanses so wide that even light itself becomes lost traveling around them. The journey for a photon from the Sun to our closest neighboring star surpasses 4 light years. Spanning the distances between galaxies takes millions of years. Realizing that these vast stretches are mere grains of sands of the cosmos fills one with wonder. So, what truly is the observable universe and how far it stretches? Our solar system is merely one among countless others scattered throughout our galaxy. It features the central star, the Sun, in its main sequence phase, orbited by 8 known planets and their moons. Beyond these larger bodies, the solar system is home to millions of smaller celestial objects, such as asteroids, comets, and meteoroids. The Moon orbits Earth at a distance of about 384,400 kilometers, which light can travel in approximately 1.3 seconds. This proximity has made the Moon the sole celestial body beyond Earth that humans have visited. Journeying outward, we reach an inner planet, Mars. Mars orbits the Sun at an average distance of about 1.5 astronomical units. An AU is the average distance from the Earth to the Sun, approximately 149.6 million kilometers or 93 million miles, which provides a useful scale for measuring distances within our solar system. Beyond Mars lies the asteroid belt, filled with millions of rocky and metallic fragments ranging from 2.1 to 3.3 AU from the Sun. This region likely represents the debris of a protoplanet, prevented from forming by Jupiter's immense gravity. Jupiter itself, the gas giant of our planetary neighborhood, orbits at about 5.2 AU. This gas giant's massive gravitational field has profoundly influenced the solar system's architecture, including its collection of diverse moons from volcanic Io to icy moon Europa. Admired for its extensive ring system, Saturn orbits the Sun at about 9.5 AU. Beyond Saturn, the solar system extends into the colder, darker realms of Uranus and Neptune. The furthest recognized planet, Neptune, orbits at about 30 astronomical units from the Sun, equivalent to 4 light hours. Remarkably, Neptune's path only covers a fraction of our solar system's vastness. Neptune's orbit, while extensive, captures only a fraction of our solar system's scope. Beyond Neptune stretches the Kuiper Belt, where dwarf planets like Pluto reside at about 39 AU from the Sun. The most distant object we've discovered so far is far out, located about 132 astronomical units away, which translates to 18 light hours. Yet, even this distant object is nowhere near the outer edge of the supposed Oort cloud, believed to extend as far as 100,000 astronomical units from our Sun, marking the boundary of our solar system's gravitational influence and the start of interstellar space. This boundary marks the edge of our Sun's gravitational influence and the beginning of interstellar space. Now traveling further to our solar system, we have empty space and space clouds. However, far beyond that, our cosmic neighborhood is rich with a variety of stars, ranging from those closest to the Sun to those on the outer edge of our immediate stellar community. Within the span of only about 20 light years, over 50 stars offer a glimpse of the universe around us. Our first stop is Proxima Centauri, located about 4.24 light-years away. This red dwarf star is orbited by at least 2 planets, one of which, Proxima b, lies within the star's habitable zone. This zone is where conditions might be right for liquid water to exist on the surface, raising possibilities about life beyond Earth. Just slightly farther away from Proxima Centauri are Alpha Centauri A and B, shining brightly at about 4.37 light-years from us. These 2 stars form a binary system, with Alpha Centauri being similar to our own Sun, and Alpha Centauri B being slightly smaller and cooler. The dynamics of this binary system provide critical insights into how planetary systems can form and evolve around similar binary pairs. Moving beyond the Alpha Centauri system, we find Barnard's star, a red dwarf about 6 light-years away. It's known for its rapid motion across the sky and stands out due to its age and activity. Although initially it was hoped to host exoplanets, searchers have so far come up with a conclusion to have no planets. Another notable neighbor is Wolf 359, located about 7.8 light-years away. This red dwarf is one of the faintest and least massive stars observed. It's a flare star, which means it undergoes sudden increases in brightness because of magnetic activity. We cannot talk about nearby stars without mentioning Sirius, the brightest star in our night sky, located about 8.6 light-years away. Sirius is a binary star system consisting of a main sequence star, Sirius A, and a faint white dwarf, Sirius B. The system is especially important for the study of white dwarf atmospheres and stellar evolution. About 11 light-years away, Ross 128, a red dwarf, is home to an Earth-sized exoplanet, Ross 128 bits. It's a prime target for studying planetary atmospheres and conditions that could support life. Luyten's star, about 12.2 light-years away, is an interesting case. It's an old red dwarf with minimal stellar activity, but it hosts at least 2 terrestrial planets. Its proximity and the characteristics of its planets make it an excellent target for direct imaging and atmospheric study in the future. Another notable mention goes to the Voisey Keti. This star is about 12 light-years away and is known for its multiple terrestrial-sized planets. What makes this system unique is the compact arrangement of its planets, which challenges our models of how planetary systems develop. Located just about 12.5 light-years away, this star was only discovered in 2003 due to its very low brightness. It has at least 2 Earth-like planets, both potentially in the habitable zone. This star system poses exciting questions about the longevity and stability of habitable conditions. Our journey would be incomplete without visiting one of the furthest neighboring stars within 20 light years. Gliese 832, located about 16 light years away, this red dwarf star hosts a planet that has garnered significant interest, Gliese 832c. Now, if we talk about our home galaxy, the Milky Way galaxy is a vast and complex structure filled with wonders and mysteries. At the heart of this immense galaxy is our solar system, located in the Orion Arm, one of the galaxy's several spiral arms. These arms, filled with stars, dust, and gas, extend outwards from the central bulge, creating the beautiful spiral pattern that is characteristic of many galaxies like ours. The Milky Way is home to approximately 400 billion stars, each with its own story and potential planetary systems. Among these stars, scientists estimate there could be over 1 trillion exoplanets orbiting stars other than our Sun. The galaxy's diameter is estimated to be around 100,000 light years, which means that light traveling at 300,000 kilometers per second would take 100,000 years to traverse from one side of the galaxy to the other. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure composed of stars. Surrounding the main disk of the Milky Way is a stellar halo, which extends even further and may be twice the diameter of the main disk. The thickness of the Milky Way's main disk is about 1,000 light years. However, in the center of the galaxy, there's a bulge where the density of stars increases dramatically. This central bulge, about 3,000 light years thick, contains a dense concentration of stars, gas, and potentially a supermassive black hole known as Sagittarius A. Within the Milky Way, our solar system is located about 27,000 light years from the galactic center, nestled in the Orion Arm. This arm is a minor spiral arm located between the larger Sagittarius and Perseus arms. The Orion Arm is home to many familiar stars and constellations visible from Earth, including the famous Orion constellation. Beyond our immediate stellar neighborhood, the Milky Way is filled with a myriad of celestial objects and phenomena. There are massive star-forming regions like the Orion Nebula, where new stars are born from clouds of gas and dust. There are also ancient star clusters, some of which are nearly as old as the galaxy itself, providing valuable clues about the early stages of the Milky Way's formation. When we look beyond our immediate galactic neighborhood, we find that the Milky Way and its companions in the local group are part of a much larger structure known as the Virgo supercluster. This supercluster is an enormous collection of galaxies, providing a glimpse into the vastness of the universe. First is the Virgo supercluster, home to over 30,000 galaxies, spans an immense area of space with a diameter of about 150 million light years. This makes it one of the largest known structures in the universe. The combined mass of all the galaxies in the Virgo supercluster is estimated to be around 250,000,000,000 solar masses. To put this in perspective, this is roughly equivalent to the mass of 1,000 Milky Way galaxies. The Virgo supercluster is not a spherical object. Instead, it is quite flattened, with about 60% of its galaxies forming a flat sheet approximately 10 million light years thick. This flat structure is due to the gravitational forces that have shaped the distribution of galaxies over billions of years. The Virgo supercluster itself is part of an even larger structure known as the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, encompasses several superclusters, including the Virgo supercluster and the Great Attractor. The Laniakea supercluster spans approximately 520 million light years, making it one of the largest known cosmic structures. The overall mass of the Laniakea supercluster is estimated to be around 100 quadrillion solar masses. This massive formation contains not just our own galaxy and its neighbors, but thousands of other galaxies, each with its own unique properties and potential for hosting life. At the heart of the Laniakea supercluster lies a region known as the Great Attractor. Located roughly 250 million light-years away from Earth, the Great Attractor acts as a gravitational focal point, drawing galaxies toward it. This region exerts a significant gravitational pull on the galaxies within the supercluster, including our own Milky Way. The Great Attractor cannot be directly observed from Earth because the plane of the Milky Way obstructs our view. This has made studying the Great Attractor a challenging task for astronomers. Despite this difficulty, scientists have inferred its existence through the motion of galaxies, which appear to be drawn toward this mysterious region. The exact nature of the Great Attractor remains an enigma. It is believed to be a dense region of space with a massive concentration of galaxies and dark matter. This concentration of mass exerts a powerful gravitational pull, influencing the motion of galaxies over vast distances. As we continue to zoom out from the Laniakea supercluster, we can see that it is part of the larger cosmic web. The cosmic web is a vast network of interconnected filaments, walls, and voids that make up the large-scale structure of the universe. These filaments are composed of galaxies and galaxy clusters stretching across billions of light-years. The cosmic web is shaped by the gravitational forces of dark matter and the expansion of the universe. Galaxies and galaxy clusters form along these filaments, while enormous voids lie in between regions with relatively few galaxies. Moreover, our observable universe stretches billions of light-years across. Not only the galaxy clusters we can detect, it also includes some objects that we are yet to discover. The observable universe includes all the matter and energy we can observe from Earth, limited by the speed of light and the age of the universe. Since the universe is about 13.8 billion years old, we can only see light that has traveled up to 13.8 billion years to reach us. However, due to the expansion of the universe, the observable universe extends much farther than 13.8 billion light-years. The radius of the observable universe is believed to be about 46.5 billion light-years, making the diameter about 93 billion light-years. To put this into perspective, light travels at a staggering speed of about 300,000 kilometers per second. Yet, even at this incredible speed, it takes light billions of years to traverse the observable universe. If you could travel at the speed of light, it would take you 93 billion years to journey from one edge of the observable universe to the other. Within this immense expanse, astronomers estimate there are about 2 trillion galaxies, each containing billions of stars. If you were to count each galaxy at a rate of 1 per second, it would take you over 63,000 years to finish counting them all. Considering each of these galaxies contains billions of stars, the sheer number of stars in the observable universe becomes mind-boggling, potentially around 200 sextillion. Despite the immense scale of the observable universe, it is only a fraction of the entire universe. The actual size of the entire universe is unknown and could be infinitely larger than the observable portion. The expansion of the universe means that objects at the edge of the observable universe are receding from us faster than the speed of light, making it impossible to observe anything beyond this horizon. One of the most significant observations in cosmology is the cosmic microwave background radiation. This faint glow of light, visible in all directions, is the remnant radiation from the Big Bang, dating back to about 380,000 years after the universe's formation. The CMB provides a snapshot of the universe at its infancy and marks the edge of the observable universe in terms of time. The universe has been expanding since the Big Bang, and this expansion affects our observations. Galaxies are moving away from each other, and the space between them is stretching. This means that the observable universe is continuously growing, as light from more distant regions has time to reach us. The discovery of dark energy, a mysterious force driving the accelerated expansion of the universe, adds another layer of complexity to our understanding. Dark energy makes up about 68% of the total energy content of the universe, causing the rate of expansion to increase over time. This accelerated expansion implies that distant galaxies will eventually move beyond our observational reach, making parts of the universe forever inaccessible. Within the observable universe, scientists believe that there are an estimated 2 trillion galaxies, each containing billions of stars. These galaxies come in various shapes and sizes, from spiral galaxies like our Milky Way to elliptical galaxies and irregular formations. The vast number of stars within these galaxies suggests that there could be countless planetary systems, many of which may harbor conditions suitable for life. One of the most profound images captured by the Hubble Space Telescope is the Hubble Deep Field, which shows a small region of the sky packed with thousands of galaxies, each a massive collection of stars, planets, and potentially life. It is believed to be about 10,000 galaxies in the picture alone. The picture includes galaxies of various ages, sizes, shapes, and colors. This image represents just a tiny fraction of the sky, highlighting the sheer number of galaxies that populate the observable universe. The detection of gravitational waves has opened a new era in astronomy. These ripples in spacetime, caused by violent cosmic events like merging black holes, provide information about phenomena that are otherwise invisible to traditional telescopes. Gravitational wave observatories allow us to explore the universe in ways previously unimaginable. The observable universe not only spans vast distances, but also immense stretches of time. When we observe distant galaxies, we are looking back in time, seeing them as they were billions of years ago. This is because light takes time to travel from these distant objects to us. The observable universe serves as a time machine, allowing us to study the history and evolution of the cosmos. Some of the most distant galaxies we observe today existed when the universe was just a few 100 million years old, providing insights into the early stages of galaxy formation. But after all of this, do you question yourself how the universe reached this point, where we can't find its boundaries stretching billions of light years across? To really answer the question, we need to go back to the birth of the universe. Potentially the answer lies there. One of the most interesting questions in cosmology is, how did the universe begin? One of the primary theories in modern cosmology is the Big Bang theory, which explains how our universe began and evolved. Imagine every star, planet, and galaxy packed into an incredibly hot and dense point. Scientists believe this is how everything started about 13.8 billion years ago. From this tiny dense point, the universe began to expand and cool. This event, known as the Big Bang, marked the beginning of the universe's growth and the vast distances we observe today. The term Big Bang can be misleading, as it suggests an explosion occurring in space. However, the Big Bang was not an explosion in space, it was an expansion of space itself. In the first fractions of a second after the Big Bang, the universe expanded exponentially in a period known as cosmic inflation. During this brief period, the universe grew from an almost infinitesimally small point to a macroscopic scale. As the universe expanded, it cooled down, allowing energy to transform into particles of matter. These particles combined to form simple elements like hydrogen and helium. Over billions of years, these elements merged under the force of gravity to form stars, galaxies, and planets. The formation of these elements occurred within the first few minutes after the Big Bang, as the universe cooled enough for protons and neutrons to form nuclei. The Big Bang theory is supported by significant evidence. One key piece is the cosmic microwave background radiation, an afterglow from the early universe. This radiation provides a snapshot of the universe just 380,000 years after the Big Bang. Before this time, the universe was so hot and dense that light could not travel freely. The uniformity and slight fluctuations in the CMB support the idea of cosmic inflation and the rapid expansion of the universe. Another piece of evidence is the redshift of galaxies. This redshift indicates that galaxies are moving away from us, showing that the universe is expanding. This was first observed by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it appears to be moving away from us, supporting the idea that the universe was once much smaller, hotter, and denser. While the Big Bang theory explains the expansion and evolution of the universe, it raises additional questions. For example, it does not explain what lies beyond the observable universe. The theory of cosmic inflation suggests a rapid expansion immediately after the Big Bang, but it leaves open questions about the nature of the universe beyond what we can observe. Before the discovery of the cosmic microwave background radiation, a competing theory known as the steady-state theory suggested that the universe had no beginning or end. Rather, it remained the same overall despite its expansion by constantly creating new matter. This theory was popular in the 1940s but lost support after the discovery of the CMB in 1965, which strongly supports the Big Bang theory. Other theories, such as the Cyclic model, suggest the universe undergoes endless cycles of expansion and contraction. After the Big Bang, the universe expanded and cooled. Initially, it was a hot, dense soup of particles. As it expanded, it cooled down, allowing particles to come together and form the first atoms. These atoms then coalesced to form the first stars and galaxies. The universe's expansion continues today, with galaxies moving away from us in all directions. To think even further back, the first long-lived particles, protons and neutrons, which make up atomic nuclei, appeared around 1/10,000th of a second after the Big Bang. Before that, there was no material as we know it. Physics allows us to trace the timeline even further back to processes that happened before any stable matter existed. The observable universe includes all the matter and energy we can observe from Earth, limited by the speed of light and the age of the universe. Since the universe is about 13.8 billion years old, we can only see light that has traveled up to 13.8 billion years to reach us. However, due to the expansion of the universe, the observable universe extends much farther than 13.8 billion light years. One of the key concepts in understanding this process is Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be known to arbitrary precision. This principle allows for the temporary creation of particles from the vacuum, as long as they disappear quickly enough to comply with the law of conservation of energy. Quantum fluctuations can cause particles to appear and then disappear shortly after. This might sound strange, but such particles have been observed in many experiments. The vacuum of space is filled with particles constantly being created and destroyed, seemingly out of nothing. This suggests that the quantum vacuum is actually something rather than nothing. Where did spacetime itself come from? To answer this, we need to go back to the very beginning, into the Planck epoch. This period was so early in the universe's history that our best theories of physics no longer work. It happened only a tiny fraction of a second after the Big Bang. During this time, space and time themselves were affected by quantum fluctuations. Usually, physicists use quantum mechanics for tiny particles and general relativity for large cosmic scales. But to understand the Planck epoch, we need a complete theory of quantum gravity that combines the two. We don't have a perfect theory of quantum gravity yet, but there are ideas like string theory and loop quantum gravity. These theories suggest that ordinary space and time come from deeper microscopic processes. What we experience as space and time is the result of quantum processes, which are hard for us to understand because we are used to the large-scale world. Quantum fluctuations happen constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a short moment, and then destroy each other. This phenomenon is known as quantum foam. But quantum fluctuations alone don't explain the universe's vast scale and complexity. There is dark energy, a mysterious force that fills all of space and accelerates the expansion of the universe. While we don't fully understand dark energy, it's believed to play a crucial role in the creation and evolution of the cosmos. So, how did we get from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded exponentially, setting the stage for the formation of galaxies, stars, and planets. Gradually, due to dark energy, these celestial objects began to push each other, rather than attracting, leading the universe's exponential expansion. Dark energy is a mysterious force that counteracts gravity and causes the universe to expand at an accelerating rate. This accelerated expansion means that galaxies are not just moving away from each other, but are doing so at increasing speeds. Eventually, this could lead to a future where galaxies move so far apart that they become isolated from each other, making the universe a much lonelier place. In conclusion, the birth and expansion of the universe involve complex processes governed by quantum mechanics and cosmic forces like dark energy. From the Big Bang and cosmic inflation to the ongoing expansion driven by dark energy, these phenomena have shaped the observable universe we see today. As our understanding of these processes grows, we continue to uncover the profound mysteries of the cosmos and our place within it. The radius of the observable universe is believed to be about 46.5 billion light-years, making the diameter about 93 billion light-years. Despite the immense scale of the observable universe, it is only a fraction of the entire universe. The actual size of the entire universe is unknown and could be infinitely larger than the observable portion. The expansion of the universe means that objects at the edge of the observable universe are receding from us faster than the speed of light, making it impossible to observe anything beyond this horizon. The universe has been expanding since the Big Bang, and this expansion affects our observations. Galaxies are moving away from each other, and the space between them is stretching. This means that the observable universe is continuously growing as light from more distant regions has time to reach us. Within the observable universe, scientists believe that there are an estimated 2 trillion galaxies, each containing billions of stars. These galaxies come in various shapes and sizes, from spiral galaxies like our Milky Way to elliptical galaxies and irregular formations. The vast number of stars within these galaxies suggests that there could be countless planetary systems, many of which may harbor conditions suitable for life. One of the most profound images captured by the Hubble Space Telescope is the Hubble Deep Field, which shows a small region of the sky packed with thousands of galaxies, each a massive collection of stars, planets, and potentially life. This image represents just a tiny fraction of the sky, highlighting the sheer number of galaxies that populate the observable universe. To understand how the universe could begin from nothing, we need to explore the strange world of quantum mechanics. In the realm of quantum physics, nothing isn't the absence of anything, but rather a state of vacuum energy where particles constantly pop in and out of existence. This phenomenon is known as quantum fluctuations. Quantum fluctuations occur in what is known as the quantum vacuum, a state with the lowest possible energy where particles can momentarily appear and then vanish. According to the laws of quantum mechanics, it is possible for these fluctuations to lead to the creation of a universe. In this context, nothing is an energetic state that can give rise to matter and energy. But after understanding how our universe began, we also need to understand how the universe reached its present state. Cosmic inflation refers to a very brief period right after the Big Bang when the universe expanded at an incredibly rapid rate. Imagine the universe as a tiny, tightly packed point that suddenly stretched out, growing at an unimaginable speed. This rapid expansion occurred in less than a fraction of a second, making the universe much larger almost instantaneously. Scientists believe that this rapid expansion was driven by a special kind of energy present in the early universe. This energy, often referred to as inflationary energy, caused space itself to stretch faster than the speed of light. Think of it like blowing up a balloon in an instant, causing it to expand from the size of a pinhead to the size of a basketball. Before inflation, the universe was a chaotic mess with random fluctuations in density and temperature. The rapid expansion spread everything out evenly, creating a smooth and uniform universe on large scales. Although inflation smoothed out the universe, it also left behind tiny irregularities or fluctuations. These small differences in density eventually grew under the influence of gravity, forming the galaxies, stars, and planets we see today. One of the most important pieces of evidence for inflation is the cosmic microwave background radiation. The CMB is the faint afterglow of the Big Bang, and it provides a snapshot of the universe when it was just 380,000 years old. The uniformity of the CMB, with its slight temperature fluctuations, matches the predictions made by the theory of inflation. The distribution of galaxies and galaxy clusters in the universe also supports the idea of inflation. The way these structures are spread out and their size scales are consistent with the tiny fluctuations left behind by inflation. The universe appears to be geometrically flat, meaning its shape follows the rules of Euclidean geometry. Inflation explains why the universe is flat, because the rapid expansion would have smoothed out any initial curvature. Inflation solves the horizon problem, which asks why different parts of the universe, so far apart from each other, have the same temperature and properties. The rapid expansion during inflation would have allowed these regions to have been in contact with each other before inflation spread them out. Inflation is driven by a hypothetical field called the inflaton field. This field, associated with a particle called the inflaton, had a very high energy density that caused the rapid expansion. As the universe expanded, the inflaton field's energy decreased, eventually leading to the end of the inflationary period. The energy from the inflaton field was then converted into particles and radiation, heating up the universe and leading to the Big Bang nucleosynthesis, where the first elements were formed. During inflation, tiny quantum fluctuations in the inflaton field were stretched to macroscopic scales. These fluctuations created slight over- and underdensities in the early universe. Over time, gravity amplified these fluctuations, leading to the formation of large-scale structures like galaxies and galaxy clusters. Cosmic inflation helps into several key aspects of the universe, including why the universe looks the same in all directions and why the cosmic microwave background radiation is so uniform. It also accounts for the flat geometry of the universe, as observed in the CMB. It also provides a mechanism for the formation of galaxies and large-scale structures from tiny initial fluctuations. Not only inflation theory suggests expansion of the universe, but there is also an extended concept of the theory known as chaotic inflation theory that explains how the early universe could have experienced a period of extremely rapid expansion. To understand chaotic inflation, let's start with a simple example. Imagine you have a magic balloon that starts very small, almost too tiny to see. Suddenly, this balloon begins to blow up at an incredibly fast rate, much faster than any normal balloon you've ever seen. As it expands, some parts of the balloon grow larger and larger, while other parts stop growing and stay the same size. This magic balloon is similar to a special part of space experiencing what we call chaotic inflation. In this theory, the universe is like a magic balloon. Some regions of space undergo rapid expansion, growing exponentially, while other regions remain static. This results in a patchy universe, where different areas expand at different rates. This patchy pattern means that the universe didn't need a perfectly uniform starting point to begin its rapid expansion. It could have started expanding from almost any kind of initial condition, whether smooth, bumpy, or something in between. Chaotic inflation explains that the universe's expansion can begin under a wide variety of conditions. Unlike the standard inflation theory, which might require specific initial states, chaotic inflation suggests that almost any kind of patch of space can suddenly start expanding rapidly. This is due to the presence of a special kind of energy field known as the inflaton field. The inflaton field can cause different regions of space to expand at different rates. In some patches, the inflaton field's energy is high, leading to rapid expansion. In other patches, the energy is lower, resulting in slower or no expansion. Over time, the rapidly expanding regions dominate, creating a universe that grows exponentially in certain areas while remaining static in others. To visualize chaotic inflation, picture the universe as a landscape with hills and valleys. The inflaton field represents this landscape, where the height of the hills and valleys corresponds to the energy level of the field. In some regions, the field has high energy, causing rapid expansion. In other regions, the energy is lower, leading to slower expansion or no expansion at all. As time progresses, the regions on top of the hills expand rapidly and dominate the landscape. These regions continue to grow, creating a universe that is both vast and varied. Chaotic inflation fits into the broader framework of the Big Bang theory by providing a mechanism for how different regions of the universe could have expanded rapidly after the initial explosion. It complements the standard inflationary model by suggesting that this rapid expansion could have occurred under a wide range of initial conditions, not requiring a perfectly uniform starting point. The resulting universe from chaotic inflation could be patchy, with some regions expanding faster than others. This patchiness can help explain the large-scale structure of the universe and the distribution of galaxies and clusters we observe today. Chaotic inflation also introduces the possibility of multiple universes or a multiverse. Since different regions of space can expand at different rates, it's conceivable that other universes with different properties could exist beyond our observable universe. So according to this theory, the universe's edge is not a single well-defined boundary, but rather a patchwork of regions that expanded at different rates. Some areas may have stretched so far that they lie beyond our current observational reach, creating a horizon that continuously shifts as the universe expands. The idea of multiple regions expanding at different rates also supports the possibility of a multiverse, where other universes with varying physical laws could exist beyond what we can see. This makes the true edge of our universe not a clear-cut boundary, but a dynamic and ever-changing frontier. To answer the question about the edge of the universe requires understanding the shape of the universe at large. For a long time, people thought the universe was shaped like a sphere. This idea goes all the way back to Aristotle. They believed the Earth was inside this sphere, separated from the rest of the universe by a boundary where space stops, similar to the edge of what we can see. But explaining what happens at this boundary is really hard, even for the smartest people and most advanced computers. It's tough to describe what a universal boundary would look like or how it would exist. We don't see any signs of such a barrier. There doesn't seem to be a place in space, except maybe black holes, where light gets stopped. So we now think that no matter the size or shape of the universe, it probably doesn't have a physical edge like the one we can observe. Instead of everything being inside a sphere, it's more like we're on the surface of one. The surface of a sphere is finite but has no edge. Think about Earth. It's limited in size, but you can fly around it forever without hitting an edge. You would never run out of Earth to fly over because gravity would just bring you back to where you started. Similarly, it's thought that the gravity of the universe's matter causes the same effect. However, when we use maths to try to describe this boundary, it gets really complicated. Even the smartest people and the most powerful computers struggle to explain what a universal boundary would look like or how it would exist. When we look into space, we don't see any signs of a boundary. Light travels freely, except near black holes where it gets trapped. This means the universe probably doesn't have a physical edge. Instead, we think of the universe like the surface of a sphere. Think about the surface of Earth. It's limited in size, but you can keep traveling around it without ever hitting an edge. Gravity just brings you back to your starting point. The universe is thought to work the same way. The gravity from all the matter in the universe bends space in such a way that you could travel forever and never find an edge. The universe could be infinite, or it could wrap around on itself like the surface of a sphere. This means you could keep traveling in one direction and eventually end up back where you started, just like on Earth. Balanced perfectly between the possibilities of a positively or negatively curved universe, there is a scenario called critical density. In this case, omega is exactly 1, meaning there are about 5.7 hydrogen atoms per cubic meter of space. At this density, the effects of gravity and dark energy balance each other out, resulting in no overall curvature, making the universe flat. A flat universe without curvature can't close itself off and is the kind of universe we would expect to be truly infinite. In this universe, space behaves like an endless, flat sheet of paper. Two parallel photons of light would remain parallel forever, traveling through new space infinitely. With gravity and dark energy in perfect balance, a flat universe is smooth and continues to expand without ever collapsing. Even though it sits on the edge of recollapse, this would only happen after an infinite amount of time, so in reality it will expand forever, like a negatively curved universe. Scientists were very interested in figuring out the shape of the universe, but how do you measure its curvature? There are two main methods. The first is by summing up the total energy densities in the universe by observing its large-scale properties. The discovery of the nearly uniform microwave sky in the 1960s suggested that the universe might be at critical density. And the discovery of cosmic acceleration in 1997 showed that space might be either negatively curved or very close to flat. The second, more accurate way to figure out the universe's shape is by studying the cosmic microwave background. This is leftover radiation from the Big Bang, acting like a snapshot of the universe when it was only 379,000 years old. If there's any curvature in the universe, we're likely to find it here. The CMB is very smooth, looking the same in all directions, with only small temperature fluctuations. These fluctuations come from density differences in the early universe. By measuring the sizes and distances between these hotspots, scientists can look for distortions in the radiation. They then draw triangles between these areas and measure the angles to determine the universe's curvature. In a positively curved universe, the angles would add up to more than 180 degrees. In a negatively curved universe, they would add up to less than 180 degrees. In a flat universe, the angles would add up to exactly 180 degrees. Using this method to map the CMB in enough detail to reveal its shape, concluding that omega is exactly 1, with a 10% margin of error, suggesting the universe might be flat. Later, NASA's Wilkinson microwave anisotropy probe provided even more precise measurements, reaffirming that the universe is largely flat and critically dense. In 2010, the European Space Agency's Planck satellite offered the most detailed dataset of the early universe, also concluding the universe is very close to flat. The question remains, why is the universe so perfectly designed or shaped? Even if the universe has a slight curvature, the fact that we can't determine it after almost 14 billion years suggests it was very close to critical at the Big Bang. This perfect balance is known as the flatness problem, and understanding it is a key goal in modern cosmology. There are three possible solutions to the flatness problem. The universe might actually be flat and infinite. It could be curved, but on such a large scale that we can't detect it, or it may have a shape that hides its true dimensions from us. The idea of an infinite universe is profound but hard to imagine, especially considering the Big Bang theory suggests a finite volume. Our universe has properties that you'd expect in a finite universe, like certain limits. For example, the Planck satellite found that the variability in the CMB's power spectrum flattens out significantly on scales larger than our observable universe. This suggests a limit that wouldn't be expected in an infinite universe. It's possible the universe has a shape that hides its true size from us with a complex structure. In conclusion, while we have evidence suggesting the universe is flat, the true shape of the universe remains one of the biggest mysteries in cosmology. While searching for the edge of the universe, we also need to understand about the center of the universe. The universe is undeniably vast, and from our perspective, it may seem like Earth is in the middle of everything. But is there a center of the cosmos, and if so, where is it? If the Big Bang started the universe, then where did it all come from, and where is it going? To start discussing these questions, let's go back about 100 years. In the 1920s, astronomer Edwin Hubble made two amazing back-to-back discoveries. Early in the decade, he found that island universes, now known as galaxies, sit very far away from us. Later that decade, he discovered that, on average, all galaxies are moving away from us. There was already a helpful theoretical explanation for this. Einstein's theory of general relativity had predicted that the universe was dynamic, either expanding or contracting. This was different from the prevailing view at the time, which was that the cosmos was perfectly static. A group of scientists working semi-independently took Einstein's equations seriously and developed a solution. This solution to Einstein's equation, together with Hubble's observations, tells us that we live in an expanding universe. On average, all galaxies are getting farther away from all other galaxies, and long ago, all the matter in the cosmos was compressed into an infinitely tiny point known as the singularity of the Big Bang. So where is the Big Bang? Surely, that would be the true center of the universe. Unfortunately, The reality we have uncovered about the universe through modern science does not lend itself to an easy explanation or even the ability to imagine it. That's because there is no center of the universe. There is no edge either. The cosmos is not expanding from anywhere, and it's not expanding into anything. In simpler terms, the Big Bang didn't happen at a single point in space. It happened everywhere in the universe at once. Imagine the universe as a balloon being inflated. Every point on the surface of the balloon moves away from every other point as it expands, but there's no center on the surface of the balloon. Similarly, our universe expands in all directions, but there's no central point from which it all began. In conclusion, while it may seem like there should be a center of the universe, the truth is that the universe has no center or edge. The Big Bang happened everywhere, and the universe continues to expand uniformly in all directions. First, let's tackle the idea of an edge. The universe includes everything that exists. Edges divide one region from another, but since the universe includes all regions, it can't have an edge. This means the universe might be infinitely big, and it's impossible to point to the center of an infinite space. Another possibility is that the universe is finite, but at very large scales, far beyond what we can observe, the universe might curve back on itself. This would mean it still doesn't have a center. Think of it like Earth. You can point to the center of the Earth's three-dimensional space, which is the molten core, but you can't point to the center of the Earth's surface. It could be any point on the surface because no point is more central than another. This means the Big Bang happened everywhere in the universe at the same time. It happened in the room you're sitting in and in the most distant galaxy we can see. The Big Bang wasn't a single point in space, it was a moment in time. It's part of the past of everything in the universe. However, there's a twist. The universe has an age, about 13.77 billion years old. Because light travels at a limited speed, we can only see a part of the universe. The edge of what we can see is about 45 billion light years away, because the universe expands faster than light. Most of the universe is hidden from us, like the beam of a flashlight in a dark forest. We can only see up to the limits of the light. From our perspective, all other galaxies seem to be moving away from the Milky Way. It seems like we are at the center of the universe, but the same can be said for any galaxy. From their perspective, they are at the center of their observable universe, and all galaxies are moving away from them. This is the nature of an expanding universe. There is no true center, but every observer, including us, can feel like they are in the middle of it all. To understand why there is no center of the universe, imagine blowing up a balloon. As the balloon inflates, every point on its surface moves away from every other point. There is no center on the surface. Every point is expanding away from each other equally. This is similar to how our universe expands. The Big Bang wasn't an explosion from a single point into empty space. It was the rapid expansion of space itself, happening everywhere at once. Now, let's talk about the observable universe. Because light travels at a finite speed, we can only see the parts of the universe from which light has had time to reach us. This creates a spherical bubble around us called the observable universe, which is about 45 billion light-years in radius. This doesn't mean the universe is only 45 billion light-years wide. It just means that's the limit of what we can see. Beyond that, the universe continues, but it's hidden from us due to the finite speed of light and the ongoing expansion of space. Imagine standing in a vast foggy field. You can only see as far as the fog allows. The edge of your vision isn't the edge of the field, just the limit of what you can see. Similarly, the observable universe is just the part we can see. The true size of the universe is much larger and possibly infinite. Because of this, every point in the universe, looks like the center from its own perspective. If you were in a galaxy billions of light years away, you would see galaxies moving away from you, just like we see from Earth. This uniform expansion makes it seem like each point is the center, but in reality, there is no central point. In the context of the universe, space itself is expanding uniformly, and every point is moving away from every other point. This means there's no single spot that can be considered the center. So does that also mean that due to expanding space, we won't be able to discover the edge of the universe? After discussing the center of the universe, we need to understand more about the edge of the universe. When we talk about the edge of the universe, it's essential to understand what we mean by edge. In everyday terms, an edge is a boundary where something ends, like the edge of a table or the edge of a piece of paper. However, when we talk about the universe, the concept of an edge becomes much more complex and fascinating. The universe includes everything that exists, all space, time, matter and energy. So, can such an all-encompassing entity have an edge? First, let's consider the idea of the universe being infinite. An infinite universe would have no boundaries, meaning it would stretch on forever in all directions. In such a universe, it would be impossible to point to a center or an edge, because every point would be just another point in an endless expanse. This is similar to the surface of a balloon that keeps expanding as you blow air into it. As the balloon inflates, every point on the surface moves away from every other point, but there is no edge on the surface itself. Each point on the balloon could be considered the center from its own perspective, but in reality, there is no central point. Now, let's think about the observable universe. This is the portion of the universe that we can see or detect. The observable universe is limited by the speed of light, which means we can only see light that has had time to travel to us since the beginning of the universe, about 13.8 billion years ago. This creates a spherical bubble around us with a radius of about 45 billion light-years called the cosmic light horizon. Beyond this horizon, light from more distant parts of the universe hasn't had enough time to reach us yet, making those regions invisible to us. The observable universe can be compared to standing in a foggy field with a flashlight. The light from the flashlight only allows you to see so far, and beyond that point, everything is hidden in the fog. This doesn't mean the field ends where your light stops. It just means you can't see beyond that point. Similarly, the observable universe is limited by how far light has traveled, but the universe itself likely continues far beyond what we can see. One common misconception is that the edge of the observable universe is the edge of the actual universe. In reality, the observable universe is just a small part of the whole universe, which could be much larger or even infinite. The cosmic microwave background acts like a wall of light, marking the edge of our observable universe. Beyond this, we can't see anything directly because the universe was opaque before this time. To understand what might lie beyond the observable universe, scientists rely on the principle of cosmological homogeneity, which states that the universe, on a large scale, is uniform and looks the same in all directions. This principle suggests that regions beyond our observable universe are likely similar to what we see within it: galaxies, stars, and cosmic structures stretching out into the unknown. If we could somehow see beyond the cosmic light horizon, we'd likely find more of the same cosmic web of galaxies and voids. To illustrate this idea further, let's imagine traveling to the edge of the observable universe. As we journey outward, we would pass through billions of galaxies, each containing billions of stars and countless planets. These galaxies are organized into clusters and superclusters, interconnected by vast filaments of dark matter and gas, forming a complex cosmic web. Eventually, we'd reach the cosmic light horizon, where the light from the earliest galaxies has taken billions of years to reach us. At this point, we'd encounter the cosmic microwave background, the faint glow of radiation left over from the Big Bang. This cosmic microwave background marks the limit of what we can observe directly, but it also provides valuable information about the early universe and the large-scale structure of the cosmos. By studying this, scientists have learned that the universe is expanding, and they can estimate its age, composition, and shape. But what if we could go even further? Beyond the cosmic light horizon, the universe continues to expand. This expansion means that distant galaxies are moving away from us at speeds faster than light due to the stretching of space itself. This doesn't violate the laws of physics because it's space that's expanding, not the galaxies moving through space. If we could travel beyond the observable universe, we'd likely find that the cosmic web continues, with more galaxies and structures similar to those we see within our observational limits. The uniformity of the CMB suggests that the universe beyond our view is much the same as the universe we can see. However, because light from these distant regions hasn't reached us, their exact nature remains a mystery. The idea of an infinite universe raises some fascinating possibilities. For instance, if the universe is truly infinite, there could be an infinite number of galaxies, stars, and planets. In such a universe, the sheer scale and variety of cosmic objects would be mind-boggling. There could be regions of the universe vastly different from our own, with different types of stars, galaxies, and perhaps even different physical laws. Another intriguing idea is the concept of a multiverse, where our universe is just one of many universes that exist. In this scenario, each universe could have its own set of physical laws and constants, leading to a diverse array of possible realities. Some theories suggest that these universes could be connected through wormholes or other exotic phenomena, allowing for the possibility of travel between them. Returning to our balloon analogy, imagine the surface of the balloon represents our universe. As the balloon expands, new regions of the surface come into view, but the surface itself has no edge. Similarly, as the universe expands, new regions of space become observable, but the universe itself remains boundless. The idea of a finite but unbounded universe is another possibility. In this scenario, the universe could be curved in such a way that it loops back on itself. This would mean that if you traveled far enough in one direction, you would eventually return to your starting point, much like traveling around the surface of the Earth. This concept is challenging to visualize because we are used to thinking in 3 dimensions, but it is a valid solution to Einstein's equations of general relativity. In such a curved universe, there would still be no edge, but the overall shape of the universe would be finite. This idea aligns with some interpretations of the cosmological principle, suggesting that the universe is homogeneous and isotropic on large scales, but curved in higher dimensions. The exact nature of this curvature, whether it is positive, negative, or flat, depends on the overall density and composition of the universe. One of the most significant discoveries in cosmology has been the detection of the universe's accelerating expansion. Observations of distant supernova and the CMB have shown that not only is the universe expanding, but this expansion is speeding up over time. This acceleration is attributed to a mysterious force known as dark energy, which makes up about 68% of the universe's total energy content. Dark energy has profound implications for the future of the universe. If the expansion continues to accelerate, galaxies will move away from each other at increasing speeds, eventually becoming isolated and invisible to each other. This cosmic isolation means that future civilizations in distant galaxies might never know about the existence of other galaxies, as they will be beyond the observable horizon. In summary, the edge of the universe is a complex and fascinating concept. While we cannot see beyond the observable universe, the principles of cosmology suggest that the universe continues much the same way beyond our observational limits. Whether the universe is infinite or finite, but unbounded, it likely has no physical edge. The expansion of the universe, driven by dark energy, means that our view of the cosmos will continue to change, revealing more about its vast and mysterious nature. To understand the concept of the cosmic light horizon more deeply, we need to discuss the oldest objects found in space. These objects are 3 actual galaxies, including GNZ11, HD1, and GLASS Z13. GNZ11 is one of the most distant galaxies ever observed. This galaxy is so far away that its light has taken 13.4 billion years to reach us, meaning we are seeing it as it was just 400 million years after the Big Bang. It's also the farthest galaxy ever discovered. HD1 is another extremely distant galaxy, located about 13.5 billion light-years away. This galaxy is significant because it provides insights into the formation of the earliest stars and galaxies. Another galaxy is the GLASS Z13, which has been observed at a distance of about 13.3 billion light-years. Like GNZ11 and HD1, this galaxy offers a glimpse into the early universe. Everything we know, see, observe, and interact with is part of what we call the observable universe. Beyond what we can see, there's likely much more out there. As time goes on, we'll be able to see more of it, as light from distant objects reaches us after traveling for billions of years. Our view of the universe depends on several factors. First, it's been 13.8 billion years since the Big Bang. Second, the speed of light, which is the fastest anything can travel, is finite and constant. Third, space itself has been expanding since the Big Bang. What we see today is the result of these factors combined with the distribution of matter and energy, all following the laws of physics. To understand what the universe was like in the past, we observe it today, measure important parameters, and use calculations to look back in time. This involves complex equations from Einstein, which cosmology students learn to solve. We've made amazing measurements about the universe. We know how fast it's expanding, the matter density, the amount of normal matter, dark energy, and smaller components like neutrinos, radiation, and black holes. By looking at this data, we can figure out how big the universe was and how fast it was expanding at any point in its history. Today, our observable universe extends about 46.1 billion light-years in all directions from us. This distance marks how far light or gravitational waves from the Big Bang would have traveled to reach us now. It's much farther than the most distant galaxy we've discovered. Simulations suggest the first stars formed between 50 and 100 million years after the Big Bang, and the first galaxies around 200 million years. We haven't seen that far back yet, but the James Webb Space Telescope might help us soon. The current record holder for the most distant galaxy is GNZ11, from when the universe was 400 million years old, just 3% of its current age. This galaxy is 32 billion light-years away, much closer than the edge of the observable universe. The reason for this difference is the universe's expansion rate has slowed dramatically over time. When galaxy GNZ11 existed, the universe was expanding 20 times faster than today. During the cosmic microwave background emission, the expansion was 20,000 times faster. At the Big Bang, it was even faster. According to our best theories, the first true galaxies formed between 120 and 210 million years after the Big Bang. corresponding to a distance of 37 to 35 billion light-years from us. This shows how rapidly the universe expanded in its early stages, with 1% of its age responsible for 20% of its total expansion. The universe's expansion stretches the light's wavelength, causing the redshift we see. The size of the universe today shows how time affects it. As time goes on, the universe will keep expanding. In the future, distances will grow so much that no galaxies beyond our local group will be visible, even with powerful telescopes. So, we should appreciate the diverse and vast universe we can see today, as it won't last forever. But how much of the unobservable universe will we be able to see in the future? The answer is, what we can currently observe is just a small fraction of the entire cosmos. This observable universe is limited by the speed of light and the age of the universe. Light from distant objects has taken billions of years to reach us, but beyond a certain point, known as the cosmic light horizon, we cannot see any further. However, as time goes on, will we be able to see more of the unobservable universe? Let's explore this fascinating question. The observable universe encompasses everything we can see or detect. It is limited by the speed of light and the age of the universe. Light from the most distant objects we can see has traveled for approximately 13.8 billion years to reach us. However, because the universe has been expanding all this time, the observable universe extends much further than 13.8 billion light-years. In fact, it reaches out to about 46.1 billion light-years in every direction. Imagine standing in a dark field with a flashlight. The light from your flashlight only allows you to see a certain distance. Beyond that point, everything is hidden in the darkness. This is similar to our observable universe. We can only see as far as light has traveled to reach us. The universe has been expanding since the Big Bang. This expansion affects our ability to see distant objects. As space itself stretches, light from distant galaxies is stretched or redshifted, making them appear further away and fainter. This redshift is a key indicator of how fast the universe is expanding. As time passes, light from more distant parts of the universe will have time to reach us. This means that the observable universe will gradually expand, allowing us to see more of the cosmos. For example, light from a galaxy 46.1 billion light-years away might reach us in the future, expanding our observable universe even further. However, there are limits to how much more we can see. The universe's expansion is accelerating due to a mysterious force known as dark energy. This acceleration means that some regions of the universe are moving away from us faster than the speed of light. Even though light from these regions is still traveling toward us, the space between us and these regions is expanding so quickly that the light may never reach us. Cosmic inflation, a rapid expansion of the universe in the first moments after the Big Bang, plays a significant role in shaping our observable universe. This inflation stretched space to such an extent that regions that were once close together were flung far apart. This process smoothed out any irregularities and led to the uniform universe we observe today. Because of inflation, there are vast regions of the universe beyond our observable horizon that were once connected to our part of the universe. These regions contain galaxies, stars, and possibly other forms of matter and energy that we cannot see. As time goes on, we may be able to observe some of these regions as light from them finally reaches us. By studying the cosmic microwave background, scientists can learn about the universe's large-scale structure and the conditions that existed in its early stages. The CMB also offers clues about the universe beyond our observable horizon. Small fluctuations in the CMB's temperature and density provide insights into the distribution of matter and energy on the largest scales. These fluctuations can help scientists infer what lies beyond the observable universe. Unobservable regions are beyond the cosmic light horizon, meaning their light hasn't had enough time to reach us. As time goes on, some of this light will eventually reach us, expanding our observable universe. However, the accelerating expansion of the universe means that some regions will remain forever unobservable. These regions are moving away from us faster than the speed of light due to the expansion of space itself. No matter how long we wait, light from these regions will never reach us. The limits of observability are defined by the combination of the universe's age, the speed of light, and the expansion rate. While we will be able to see more of the universe over time, there will always be regions that remain beyond our reach. The observable universe will continue to expand, but the unobservable universe will always be much larger. After the Big Bang, the universe was filled with different types of matter and energy and expanded rapidly. The expansion rate and gravity's pull are the two main factors shaping the universe. Expansion pushes everything apart, stretching space and separating galaxies. Gravity, on the other hand, pulls everything together. Normal matter, dark energy, radiation, neutrinos, black holes, and gravitational waves all influence this expansion. The expansion rate started high but has been slowing down because, as the universe expands, its volume increases and energy density decreases. As the density drops, so does the expansion rate, allowing light from distant objects to eventually reach us. Over time, galaxies that were once too far away to see will come into view. Even though the Big Bang happened 13.8 billion years ago, the expansion of the universe means that objects up to 46.1 billion light-years away are just now becoming visible to us. Within this observable universe, there are about 2 trillion galaxies. Despite this large number, our observations don't show an edge in space in any direction. The time since the Big Bang, the speed of light, and the ingredients in the universe determine what we can observe. Anything farther away than 46.1 billion light-years is currently beyond our reach, even if it started moving toward us at the speed of light from the moment of the Big Bang. However, this will change over time. As time passes, light from more distant objects will reach us, revealing more of the universe. You might think that if we waited long enough, we could see an unlimited amount of the universe, but that's not true in a universe with dark energy. Dark energy prevents the expansion rate from dropping to zero. But how much of the unobservable universe will we be able to see in the future? The answer is, what we can currently observe is just a small fraction of the entire cosmos. This observable universe is limited by the speed of light and the age of the universe. Light from distant objects has taken billions of years to reach us, but beyond a certain point, known as the cosmic light horizon, we cannot see any further. However, as time goes on, will we be able to see more of the unobservable universe? Let's explore this fascinating question. The observable universe encompasses everything we can see or detect. It is limited by the speed of light and the age of the universe. Light from the most distant objects we can see has traveled for approximately 13.8 billion years to reach us. However, because the universe has been expanding all this time, the observable universe extends much further than 13.8 billion light-years. In fact, it reaches out to about 46.1 billion light-years in every direction. Imagine standing in a dark field with a flashlight. The light from your flashlight only allows you to see a certain distance. Beyond that point, everything is hidden in the darkness. This is similar to our observable universe. We can only see as far as light has traveled to reach us. The universe has been expanding since the Big Bang. This expansion affects our ability to see distant objects. As space itself stretches, light from distant galaxies is stretched or redshifted, making them appear further away and fainter. This redshift is a key indicator of how fast the universe is expanding. As time passes, light from more distant parts of the universe will have time to reach us. This means that the observable universe will gradually expand, allowing us to see more of the cosmos. For example, light from a galaxy 46.1 billion light-years away might reach us in the future, expanding our observable universe even further. However, there are limits to how much more we can see. The universe's expansion is accelerating due to a mysterious force known as dark energy. This acceleration means that some regions of the universe are moving away from us faster than the speed of light. Even though light from these regions is still traveling toward us, the space between us and these regions is expanding so quickly that the light may never reach us. Cosmic inflation, a rapid expansion of the universe in the first moments after the Big Bang, plays a significant role in shaping our observable universe. This inflation stretched space to such an extent that regions that were once close together were flung far apart. This process smoothed out any irregularities and led to the uniform universe we observe today. Because of inflation, there are vast regions of the universe beyond our observable horizon that were once connected to our part of the universe. These regions contain galaxies, stars, and possibly other forms of matter and energy that we cannot see. As time goes on, we may be able to observe some of these regions as light from them finally reaches us. Measuring distances in space is fascinating. Unlike measuring distances on Earth, we can't just use a ruler or tape measure. Instead, astronomers use a variety of methods and tools to determine how far away objects like stars, planets, and galaxies are from us. These methods rely on the properties of light, the movement of celestial objects, and mathematical calculations. In this script, we'll explore the different techniques used to measure cosmic distances and how they help us understand the vastness of the universe. Accurate distance measurements also allow us to calculate the age of the universe and study about the expansion of space and the behavior of dark energy. One of the fundamental methods for measuring distances to nearby stars is parallax. Parallax is the apparent shift in the position of an object when viewed from different locations. You can see this effect by holding your thumb out at arm's length and looking at it with one eye closed, then switching eyes. Your thumb appears to move against the background. This same principle is used to measure the distances to stars. Astronomers use the Earth's orbit around the Sun as a baseline. By observing a star's position at different times of the year, they can measure the tiny shift in its position against the background of more distant stars. This shift is called the parallax angle. The smaller the angle, the further away the star is. Parallax is most effective for stars within a few hundred light-years of Earth. For more distant objects, other methods are needed. To measure distances using parallax, astronomers use a unit called the parsec. 1 parsec is the distance at which a star would show a parallax angle of 1 arcsecond. A parsec is equivalent to about 3.26 light-years, or about 31 trillion kilometers. The term parsec combines parallax and arcsecond. For objects beyond the reach of parallax measurements, astronomers use standard candles. A standard candle is an astronomical object with a known luminosity or intrinsic brightness. By comparing the known luminosity to the observed brightness, they can calculate the distance. This method relies on the inverse square law of light, which states that the brightness of an object decreases with the square of the distance from the observer. One of the most important standard candles is the Cepheid variable star. Cepheid variables are pulsating stars whose brightness varies in a regular pattern. The period of their brightness variations is directly related to their luminosity. By measuring the period of a satellite's pulsations, astronomers can determine its luminosity. Comparing this to the observed brightness allows them to calculate the star's distance. Cepheid variables are crucial for measuring distances within our galaxy and to nearby galaxies. Another valuable standard candle is the Type I supernova. These supernovae occur in binary star systems, where one star is a white dwarf. When the white dwarf accretes enough material from its companion star, it reaches a critical mass and explodes in a bright supernova. Type I supernova have a consistent peak luminosity, making them excellent standard candles for measuring distances to faraway galaxies. Edwin Hubble made a groundbreaking discovery in the 1920s. He observed that galaxies are moving away from us, and the further away they are, the faster they are receding. This relationship is known as Hubble's law. It can be expressed as: by measuring the redshift of a galaxy's light, astronomers can determine its velocity. Redshift occurs because the wavelength of light stretches as the galaxy moves away from us, making the light appear redder. Using Hubble's law, they can then calculate a galaxy's distance. This method is particularly useful for measuring distances to galaxies millions or billions of light years away. Redshift is a crucial tool for measuring cosmic distances. It occurs when the wavelength of light from an object is stretched due to the expansion of the universe, making the light appear redder. The greater the redshift, the further away the object is and the faster it is moving away from us. By measuring the redshift of a galaxy's light, astronomers can determine its velocity and, using Hubble's law, calculate its distance. The methods described above form what is known as the cosmic distance ladder. This ladder consists of different rungs, each representing a method for measuring distances over different scales. The lower rungs, like parallax, are used for nearby objects. The middle rungs, like standard candles, extend to more distant objects. The upper rungs, like redshift and Hubble's law, reach the furthest parts of the observable universe. Each rung of the ladder builds upon the previous one, allowing astronomers to measure distances across vast scales. For example, parallax measurements calibrate the distances to Cepheid variables, which in turn calibrate the distances to Type I supernova, and so on. This hierarchical approach ensures accuracy and consistency in measuring cosmic distances. Gravitational lensing is another method used to measure cosmic distances. It occurs when the gravitational field of a massive object, like a galaxy cluster, bends the light from a more distant object. This effect, predicted by Einstein's theory of general relativity, can magnify and distort the light, creating multiple images of the distant object. By analyzing the properties of the lens images, astronomers can determine the mass of the lensing object and the distance to both the lens and the background object. Gravitational lensing provides valuable information about the distribution of mass in the universe, including dark matter, and helps refine distance measurements. The cosmic microwave background is the oldest light in the universe, dating back to about 380,000 years after the Big Bang. It provides a snapshot of the early universe and contains valuable information about its size, shape, and composition. By studying the CMB, scientists can infer the distance to the edge of the observable universe and learn about the large-scale structure of the cosmos. The CMB also serves as a reference point for measuring other cosmic distances. For example, observations of the CMB helped refine the value of the Hubble constant, improving the accuracy of distance measurements across the universe. These are some of the techniques for measuring cosmic distances. Basic trigonometry, similar to what you studied in high school maths class, can be used for measuring things that are quite close, such as those in our solar system, and even in our small neighborhood of the Milky Way within 100 light-years. With the help of the parallax method, the distance of faraway objects can be measured or estimated. Imagine looking at your finger through your left eye while closing your right eye, then switching eyes. You would notice that the position of your finger seems to change with respect to a point on the wall. This is called parallax. By measuring this small change and knowing the distance between your eyes, you can calculate the distance to your finger using trigonometry. When it comes to measuring distances to other stars, the orbit of Earth around the Sun provides the baseline for these calculations. Simply, if you take a star's position once a year at one point in the sky, and then again 6 months later, you will have a relative position of the nearby object in relation to the far more distant stars in the sky. Thanks to the Pythagorean theorem, you can determine the distance if you know the size of Earth's orbit and the angle of light in those two measurements. Once trigonometry is no longer a useful technique, astronomers look for Cepheid stars, which are extremely bright and common stars. These specific stars were first identified in 1794 and have an ability to pulse, becoming dimmer and brighter in predictable cycles. Surprisingly, the longer a Cepheid takes to pulse, the brighter the star is in reality. Similarly, the shorter the pulsation duration, the dimmer the Cepheid. These pulsations are directly related to their absolute luminosity, occurring within well-defined and predictable time periods ranging from 1 to 100 days. Just like if you saw a candle right in front of you and another very far away, the one closer to you would appear much brighter. Hence, the true brightness of these stars can be determined, and consequently their distance, by measuring nearby Cepheids and comparing the length of their pulsation period to those of Cepheids that are farther away. Cepheid variables can be seen and measured to a distance of about 20 million light-years, compared to a maximum distance of about 65 light-years for Earth-based parallax measurements and just over 3,260 light-years for the Hipparcos mission. They serve as standard distance markers, constituting yet another crucial step on the cosmic distance ladder. Even though 20 million light-years sounds like an enormous distance, the cosmos is 1,000 times bigger. Thus, we need to add another step to the ladder. This is when supernovae, especially those from specific binary star systems, come in rather handy. One star in these two star systems dies and turns into a white dwarf, while the other star continues to exist. After that, the white dwarf starts to consume the surviving star and gets bigger until it has roughly 1.4 times the mass of the Sun. At that moment, there is a massive explosion that releases more energy than entire galaxies and is visible over half of the observable universe. We refer to this as a type Ia supernova. Astronomers can determine the absolute brightness of the explosion and consequently the approximate cosmic distance to those distant galaxies because we know how much mass is exploding. At even greater distances into the tens of billions of light-years, the Hubble constant comes into play. Named after Edwin Hubble, this is the unit of measurement for the expansion of the universe. The universe has been getting bigger since the Big Bang kick-started the growth. The universe is expanding, and the rate of this expansion is determined by the Hubble constant. The farther away a galaxy is, the faster it appears to be moving away from us. This phenomenon is known as redshift, which is similar to the Doppler effect experienced with sound waves. Redshift occurs because waves, which are affected by their motion through space and air, carry both sound and light. Sound travels through the air at a maximum speed of 750 miles per hour or 1,200 kilometers per hour. The sound waves in front of an ambulance get compressed as it rushes forward and blares its siren. The sound waves behind the ambulance, meanwhile, begin to spread. This means the frequency of the sound waves is higher ahead of the ambulance and lower behind it. pitch shifts are interpreted by our brains as variations in the frequency of sound waves. Similar to sound, light is a wave that moves at a fixed speed of 186,000 miles per second or 300,000 kilometers per second or around 1 billion kilometers per hour. Thus, light follows the same rules as sound. Galaxies are, as we know, moving away from us. Similar to how an inflated balloon would cause a wave created on its fabric to be stretched, the wavelength of light is stretched when galaxies move away from us. Through the use of a prism or a comparable telescope-suitable instrument like diffraction gratings, we can see an array of absorption lines from elements like sodium, hydrogen, and so on. All those absorption lines, however, experience a Doppler shift and go toward the red portion of the spectrum if that galaxy is speeding away from us. We refer to this as redshift. The opposite occurs for galaxies that are moving toward us. They are blue-shifted. Astronomers usually only use the phrase redshift to make things simpler. If a blue shift is occurring, they simply place a negative sign in front of it. A galaxy's redshift increases with its distance from Earth. As a result, the redshift of a galaxy at the cosmic light horizon, the outer end of our observable universe, is nearly infinite. This indicates that the light coming from that distant galaxy has very little energy, which is why we can hardly see those galaxies with the visible light spectrum. When Hubble looked at the light from distant galaxies through a prism, he observed a redshift away from known variables for the color. Hubble discovered that nearly all the galaxies he examined had this redshift, indicating that they were traveling away from us. Extremely far galaxy distances could be determined with a fair degree of accuracy by plotting various redshifts and known distances on a graph. Measuring distances in space is fascinating. Unlike measuring distances on Earth, we can't just use a ruler or tape measure. Instead, astronomers use a variety of methods and tools to determine how far away objects like stars, planets, and galaxies are from us. These methods rely on the properties of light, the movement of celestial objects, and mathematical calculations. In this script, we'll explore the different techniques used to measure cosmic distances and how they help us understand the vastness of the universe. Accurate distance measurements also allow us to calculate the age of the universe and study about the expansion of space and the behavior of dark energy. One of the fundamental methods for measuring distances to nearby stars is parallax. Parallax is the apparent shift in the position of an object when viewed from different locations. You can see this effect by holding your thumb out at arm's length and looking at it with one eye closed, then switching eyes. Your thumb appears to move against the background. This same principle is used to measure the distances to stars. Astronomers use the Earth's orbit around the Sun as a baseline. By observing a star's position at different times of the year, they can measure the tiny shift in its position against the background of more distant stars. This shift is called the parallax angle. The smaller the angle, the further away the star is. Parallax is most effective for stars within a few hundred light-years of Earth. For more distant objects, other methods are needed. To measure distances using parallax, astronomers use a unit called the parsec. 1 parsec is the distance at which a star would show a parallax angle of 1 arcsecond. A parsec is equivalent to about 3.26 light-years, or about 31 trillion kilometers. The term parsec combines parallax and arcsecond. For objects beyond the reach of parallax measurements, astronomers use standard candles. A standard candle is an astronomical object with a known luminosity or intrinsic brightness. By comparing the known luminosity to the observed brightness, they can calculate the distance. This method relies on the inverse square law of light, which states that the brightness of an object decreases with the square of the distance from the observer. One of the most important standard candles is the Cepheid variable star. Cepheid variables are pulsating stars whose brightness varies in a regular pattern. The period of their brightness variations is directly related to their luminosity. By measuring the period of a Cepheid's pulsations, astronomers can determine its luminosity. Comparing this to the observed brightness allows them to calculate the star's distance. Cepheid variables are crucial for measuring distances within our galaxy and to nearby galaxies. Another valuable standard candle is the Type I supernova. These supernovae occur in binary star systems, where one star is a white dwarf. When the white dwarf accretes enough material from its companion star, it reaches a critical mass and explodes in a bright supernova. Type I supernova have a consistent peak luminosity, making them excellent standard candles for measuring distances to faraway galaxies. Edwin Hubble made a groundbreaking discovery in the 1920s. He observed that galaxies are moving away from us, and the further away they are, the faster they are receding. This relationship is known as Hubble's law. It can be expressed as: by measuring the redshift of a galaxy's light, astronomers can determine its velocity. Redshift occurs because the wavelength of light stretches as the galaxy moves away from us, making the light appear redder. Using Hubble's law, they can then calculate a galaxy's distance. This method is particularly useful for measuring distances to galaxies millions or billions of light years away. Redshift is a crucial tool for measuring cosmic distances. It occurs when the wavelength of light from an object is stretched due to the expansion of the universe, making the light appear redder. The greater the redshift, the further away the object is and the faster it is moving away from us. By measuring the redshift of a galaxy's light, astronomers can determine its velocity and, using Hubble's law, calculate its distance. The methods described above form what is known as the cosmic distance ladder. This ladder consists of different rungs, each representing a method for measuring distances over different scales. The lower rungs, like parallax, are used for nearby objects. The middle rungs, like standard candles, extend to more distant objects. The upper rungs, like redshift and Hubble's law, reach the furthest parts of the observable universe. Each rung of the ladder builds upon the previous one, allowing astronomers to measure distances across vast scales. For example, parallax measurements calibrate the distances to Cepheid variables, which in turn calibrate the distances to Type I supernova, and so on. This hierarchical approach ensures accuracy and consistency in measuring cosmic distances. Gravitational lensing is another method used to measure cosmic distances. It occurs when the gravitational field of a massive object, like a galaxy cluster, bends the light from a more distant object. This effect, predicted by Einstein's theory of general relativity, can magnify and distort the light, creating multiple images of the distant object. By analyzing the properties of the lens images, astronomers can determine the mass of the lensing object and the distance to both the lens and the background object. Gravitational lensing provides valuable information about the distribution of mass in the universe, including dark matter, and helps refine distance measurements. The cosmic microwave background is the oldest light in the universe, dating back to about 380,000 years after the Big Bang. It provides a snapshot of the early universe and contains valuable information about its size, shape, and composition. By studying the CMB, scientists can infer the distance to the edge of the observable universe and learn about the large-scale structure of the cosmos. The CMB also serves as a reference point for measuring other cosmic distances. For example, observations of the CMB helped refine the value of the Hubble constant, improving the accuracy of distance measurements across the universe. These are some of the techniques for measuring cosmic distances. Basic trigonometry, similar to what you studied in high school maths class, can be used for measuring things that are quite close, such as those in our solar system, and even in our small neighborhood of the Milky Way within 100 light years. With the help of the parallax method, the distance of faraway objects can be measured or estimated. Imagine looking at your finger through your left eye while closing your right eye, then switching eyes. You would notice that the position of your finger seems to change with respect to a point on the wall. This is called parallax. By measuring this small change and knowing the distance between your eyes, you can calculate the distance to your finger using trigonometry. When it comes to measuring distances to other stars, the orbit of Earth around the Sun provides the baseline for these calculations. Simply, if you take a star's position once a year at one point in the sky, and then again 6 months later, you will have a relative position of the nearby object in relation to the far more distant stars in the sky. Thanks to the Pythagorean theorem, you can determine the distance if you know the size of Earth's orbit and the angle of light in those two measurements. Once trigonometry is no longer a useful technique, astronomers look for Cepheid stars, which are extremely bright and common stars. These specific stars were first identified in 1794 and have an ability to pulse, becoming dimmer and brighter in predictable cycles. Surprisingly, the longer a Cepheid takes to pulse, the brighter the star is in reality. Similarly, the shorter the pulsation duration, the dimmer the Cepheid. These pulsations are directly related to their absolute luminosity, occurring within well-defined and predictable time periods ranging from 1 to 100 days. Just like if you saw a candle right in front of you and another very far away, the one closer to you would appear much brighter. Hence, the true brightness of these stars can be determined, and consequently their distance, by measuring nearby Cepheids and comparing the length of their pulsation period to those of Cepheids that are farther away. Cepheid variables can be seen and measured to a distance of about 20 million light years, compared to a maximum distance of about 65 light years for Earth-based parallax measurements and just over 3,260 light years for the Hipparcos mission. They serve as standard distance markers, constituting yet another crucial step on the cosmic distance ladder. Even though 20 million light years sounds like an enormous distance, the cosmos is 1,000 times bigger. Thus, we need to add another step to the ladder. This is when supernovae, especially those from specific binary star systems, come in rather handy. One star in these two star systems dies and turns into a white dwarf, while the other star continues to exist. After that, the white dwarf starts to consume the surviving star and gets bigger until it has roughly 1.4 times the mass of the Sun. At that moment, there is a massive explosion that releases more energy than entire galaxies and is visible over half of the observable universe. We refer to this as a Type Ia supernova. Astronomers can determine the absolute brightness of the explosion and consequently the approximate cosmic distance to those distant galaxies because we know how much mass is exploding. At even greater distances into the tens of billions of light years, the Hubble constant comes into play. Named after Edwin Hubble, this is the unit of measurement for the expansion of the universe. The universe has been getting bigger since the Big Bang kick-started the growth. The universe is expanding, and the rate of this expansion is determined by the Hubble constant. The farther away a galaxy is, the faster it appears to be moving away from us. This phenomenon is known as redshift, which is similar to the Doppler effect experienced with sound waves. Redshift occurs because waves, which are affected by their motion through space and air, carry both sound and light. Sound travels through the air at a maximum speed of 750 miles per hour or 1,200 kilometers per hour. The sound waves in front of an ambulance get compressed as it rushes forward and blares its siren. The sound waves behind the ambulance, meanwhile, begin to spread. This means the frequency of the sound waves is higher ahead of the ambulance and lower behind it. pitch shifts are interpreted by our brains as variations in the frequency of sound waves. Similar to sound, light is a wave that moves at a fixed speed of 186,000 miles per second or 300,000 kilometers per second or around 1 billion kilometers per hour. Thus, light follows the same rules as sound. Galaxies are, as we know, moving away from us. Similar to how an inflated balloon would cause a wave created on its fabric to be stretched, the wavelength of light is stretched when galaxies move away from us. Through the use of a prism or a comparable telescope suitable instrument like diffraction gratings, we can see an array of absorption lines from elements like sodium, hydrogen, and so on. All those absorption lines, however, experience a Doppler shift and go toward the red portion of the spectrum if that galaxy is speeding away from us. We refer to this as redshift. The opposite occurs for galaxies that are moving toward us. They are blue shifted. Astronomers usually only use the phrase redshift to make things simpler. If a blue shift is occurring, they simply place a negative sign in front of it. A galaxy's redshift increases with its distance from Earth. As a result, the redshift of a galaxy at the cosmic light horizon, the outer end of our observable universe, is nearly infinite. This indicates that the light coming from that distant galaxy has very little energy, which is why we can hardly see those galaxies with the visible light spectrum. When Hubble looked at the light from distant galaxies through a prism, he observed a redshift away from known variables for the color. Hubble discovered that nearly all the galaxies he examined had this redshift, indicating that they were traveling away from us. Extremely far galaxy distances could be determined with a fair degree of accuracy by plotting various redshifts and known distances on a graph. Back in the 4th century BCE, a Greek scholar named Archytas imagined reaching the edge of the universe and trying to extend his hand further. He believed that if there was nothing beyond, then the universe must be infinite. In the 16th century, an Italian philosopher named Giordano Bruno also believed that the universe was infinite and full of countless stars and planets. In the 17th century, English philosopher Thomas Hobbes thought it was pointless to speculate about an infinite universe beyond what we can see because we couldn't measure or understand it. He suggested that people should focus on what could be observed and understood instead. His practical approach has influenced scientists even today, who often say that speculating on such matters is not very useful. Despite the risks of getting lost in such deep questions, some modern cosmologists continue to explore these ideas with the help of today's technology and centuries of accumulated knowledge in science, math, and philosophy. Our understanding of the universe is like looking out from an island where we can only see as far as the horizon. Light travels at a constant speed, so when we look into space, we're also looking back in time. We can see galaxies that existed 1 billion, 5 billion, or even 10 billion years ago. The edge of what we can observe is defined by this limit in time, not just space. It's like a marker of how far light has traveled since the earliest galaxies appeared. Those first galaxies, whose light has been traveling for 13.8 billion years, are now much farther away, which is about 46 billion light-years due to the expansion of the universe. When we look as far as we can into the universe, there's nothing about the distant galaxies that suggests they're hitting against any kind of boundary. Despite early expectations of a universe that began unevenly, what we actually see on a large scale is surprisingly uniform. Space appears to be expanding uniformly in all directions without a central point. On scales larger than about 230 million light-years, everywhere we look is roughly the same. There are no regions significantly hotter, colder, or more crowded with galaxies than others. Despite the universe's apparent vastness being 92 billion light-years across, The uniformity suggests it might be even larger to accommodate any initial imperfections that inflation smoothed over. However, as an English philosopher Thomas Hobbes pointed out, there's a limit to what we can learn about these distant regions. No technology can overcome the barriers set by the speed of light. Nevertheless, we possess boundless imagination, and it's within our nature to ponder what might lie beyond the visible universe, even if such speculation might not lead to concrete answers. Imagine a person from the Amazon tribe venturing into the ocean. If he sails long enough, he might end up back where he started without ever encountering a boundary or edge. This is because the Earth is round. Its surface curves back on itself, creating a finite but edgeless 2D space. Cosmologists suggest our 3D universe might be similarly curved in such a way that it's finite yet has no edges. Testing this idea involves understanding how geometry works in different spaces. On a flat surface, parallel lines stay parallel forever. On a sphere, like Earth, parallel lines eventually meet. On a saddle-shaped surface, parallel lines spread apart. Back in the 1930s, Edwin Hubble tried to apply this logic to the universe by counting galaxies along a line of sight to see how their number changed with distance. However, because looking farther into space also means looking back in time, the evolution of galaxies complicates these counts. Today, astronomers use better methods and tools, like standard rulers, to compare their models of the universe's shape with what we observe. Projects like the Wilkinson Microwave Anisotropy Probe have measured the total mass and energy in the universe, comparing it to critical values that would determine whether the universe will expand forever or eventually collapse. By examining slight irregularities in the cosmic microwave background that fills space, astronomers look for any signs of curvature. Discovering whether space is curved positively or negatively, or even a mix of both, would help us understand the true size and shape of the universe, supporting the idea of a finite but boundaryless cosmos. In a similar way, the instruments scientists use to observe the universe have their limits. This suggests that while the universe appears flat from our current perspective, we might not be high enough to see its true shape. The flatness we observe sets a minimum size for the part of the universe we can't see. If the universe does have a curve but appears flat, it must be at least 37 trillion light-years in diameter, thousands of times larger than the part we can observe. It's a large distance, and it's just the smallest possible size. The universe could be even larger, perhaps even infinite. In 1980, Mandelbrot was one of the first to use computer graphics to visualize concepts that couldn't be easily drawn by hand. He used simple equations to create images of a new type of geometry he called fractal, from the Latin word meaning broken or shattered glass. Fractals are structures that look similar no matter how much you zoom in or out, always revealing more detail and never becoming simpler. This means they have endless complexity. Using computers, Mandelbrot created what is now known as the Mandelbrot set to demonstrate this idea. But he also pointed out that similar patterns are found in nature, like in fern leaves, and even in the way galaxies cluster together. He wondered if the entire universe might be a fractal, although we now know that at the largest scales we can see, the universe looks mostly the same everywhere. But could there be fractal-like patterns beyond what we can currently observe? While we might not be able to answer how far the universe stretches beyond our observable limits right now, even starting with what we can see, we quickly encounter the idea of infinity once more. Our universe is expanding, with everything moving away from everything else, much like a loaf of bread rising in an oven. If the universe started from an infinite point, our observable universe was just a small part of that infinite expanse. Over time, although our observable universe gets bigger, It's really just a measure of how far light has traveled over time. The actual physical universe is becoming less dense. While larger structures like galaxies are held together by gravity, every galaxy beyond our local group is drifting further away at an average rate of 70 km per megaparsec. Looking into the future, if no new forces interfere, the universe will continue to expand. Galaxies will drift further apart, and eventually, even stars will move away from each other, leading to a state known as the heat death of the universe. However, there is no single event that will end the universe. Our observable universe will keep expanding, potentially becoming infinitely large. Because of the nature of infinity, it would take an infinite amount of time to reach this state, and we would still only be able to explore a finite part of it, since the universe expands faster than we can explore it. When we look back in time, the expansion of the universe reverses. The universe gets smaller, denser, and hotter, until it doesn't resemble the universe we know today. At this stage, the laws of physics start to behave in strange ways. We can only start to understand the universe once it becomes larger than 1 Planck length. At sizes smaller than this, our known physics doesn't work anymore. The universe might have started expanding from a point that was infinitely small, dense, and hot. We don't know what this would look like or how it would behave. Our observations and models don't suggest any other kind of beginning. Thinking about the universe being infinitely old and expanding from a point that was infinitely small challenges our understanding. Based on what we see now, we can't disprove the theory that the universe could keep expanding forever. This raises questions about how we reconcile our models of the Big Bang with the idea of an infinitely large universe. The universe we can see is expanding, but that might not be true for the entire universe all the time. Cosmologists like Alan Guth and later Andre Linde have suggested that what we see might just be a small, inflating region within an infinitely large universe. This concept, known as eternal inflation, proposed in 1979, suggests that our universe is just one of countless bubble universes within an endless cosmic expanse. Each of these bubble universes could be at a different stage of development and might even operate under different physical laws. This idea leads to the concept of a multiverse, where endless universes exist, each potentially with its own set of physical rules. Exploring these theories introduces even more complexity, especially when considering theories like M-theory, a type of string theory. This theory suggests our reality is just one of many layers, existing briefly where dimensions intersect within a vast hyperspace. We then have to think about not just infinite universes in our 3 dimensions, but a multiverse with countless dimensional combinations. Each of these universes could have different physical constants, like gravity or particle mass, opening up limitless possibilities. Our Big Bang might just be one small detail, and the eventual heat death of our universe one large detail in a much greater scheme. Roger Penrose's idea of conformal cyclic cosmology adds another layer. He suggests that when our universe seems infinitely large, it might actually be starting a new universe on a completely different scale. According to these researchers, our universe might be just one bubble within a sea of many universes whose physical laws differ from patch to patch, spanning all physical possibilities. British physicist Brian Cox has discussed how the idea of multiple universes existing simultaneously fits within the framework of what's known as eternal inflation. This theory expands on the concept of the Big Bang, suggesting that the universe we observe is just one of many bubbles in a frothy sea of space-time. These bubble universes are not static, but are continually being formed. The formation process of each bubble universe begins when a particular region of space stops its rapid inflation. However, eternal inflation theory suggests that not all parts of spacetime cease to inflate at the same time. Some regions continue to undergo inflation, leading to the perpetual creation of new universes. Each of these universes can have entirely different physical laws, potentially unlike anything we can observe on our own. To better visualize the multiverse theory, imagine it as an immense library filled with a vast number of books. Each book in this library represents a different universe. If this library truly contains an infinite number of books, then every possibility exists in one of them. In one of these stories, for instance, the physical constants we take for granted, like gravity or the speed of light, might be altered slightly. In one book, gravity could be weaker, making creatures grow taller and buildings potentially loftier. In another, the speed of light might be slower, profoundly affecting the way light and energy move through that universe. But the variations between these universes extend beyond just the physical laws. They could include entirely different courses of history and evolution. Imagine a universe where the dinosaurs never faced extinction, allowing them to evolve into the dominant sentient species. Or consider a universe where the fundamental elements of matter differ, leading to planets and stars composed of substances like dark matter. But is there any evidence of a multiverse? Or are we one of a bubble in the multiverse? In the book Endless Universe Beyond the Big Bang, authors Paul Steinhardt and Neil Turok propose an idea. They hypothesized that the universe didn't begin with a single Big Bang. Instead, they suggest a model involving endless cycles of cosmic events, possibly including collisions with other bubble universes. This theory aligns with the findings of researcher Rhonda Ramcherry in 2015, who proposed that our universe might have bumped into another universe. Cherry's study of the cosmic microwave background radiation revealed unusual signals that could hint at such a cosmic interaction, though whether this contact was minor or significant remains unclear. The CMB, often called the afterglow of the Big Bang, is essentially the oldest light detectable with modern instruments. It's like a snapshot of the universe's infancy, captured billions of years ago, which helps scientists piece together how the universe has expanded and evolved. This leads us to consider how the CMB might indicate the existence of a multiverse. When astronomers analyze the CMB, they observe not just a consistent glow, but a complex pattern of light and dark patches. These patches show minute temperature differences that play a key role in the formation of the universe's large-scale structure as we know it today. However, some features within the CMB, like the cold spot, an expansive area of lower than average temperatures, have mystified researchers. One intriguing theory about the cold spot is that it might be a sort of cosmic bruise, a remnant from a time when our universe came into close contact with another universe. This hypothesis suggests that such interactions could be evidence of multiple universes brushing against each other, supporting the broader concept of a multiverse where our universe is just one of many. In 2007, theoretical physicist Laura Massini-Holton and her team put forward a hypothesis about the cold spot observed in the cosmic microwave background. They suggested that this large, colder region could be evidence of our universe having interacted with another universe. According to their theory, if multiple universes exist, they might occasionally collide, and such collisions could leave detectable marks, much like bruises. Laura Massini proposes that the cold spot may be one of these cosmic bruises caused by the gravitational effects of an adjacent universe. This nearby universe could have exerted a gravitational pull strong enough to slightly slow down the expansion in that specific area of our universe, resulting in the cooler temperatures we observe today. This idea aligns closely with findings by Rhonda Ramcherry in 2015. Cherry suggested certain unusual features in the CMB as potential signs of a past collision with another universe, describing them as a bruise from such an encounter. Massini-Holton also suggests that the interaction between universes could cause inflation to fluctuate, leaving behind scars or dents in the fabric of our cosmos. She believes that these scars from the inter-universe interactions might be visible as anomalies like the cold spot. Fast forward to more recent times, these hypotheses lead to predictions about what other similar anomalies might look like. One key aspect of cosmic inflation theory is the expectation that everything in the universe should be uniformly distributed across the sky. However, the presence of anomalies like the cold spot challenges this notion, suggesting a potentially more complex history of our universe. These observations and theories bring up profound questions about the very nature of our universe. They challenge the traditional view that the Big Bang was the absolute beginning. Instead, they raise possibilities that the Big Bang could have been a transitional phase from a previous universe, or perhaps the universe existed in some form even before the events that we consider the beginning. The anomalies observed in the cosmic microwave background radiation suggest that our understanding of the universe's origin might need to be revised to favor these new ideas. Sir Roger Penrose's conformal cyclic cosmology model presents a vision of the universe where each cycle or epoch starts with a Big Bang and is followed by a period of expansion. During this phase, matter and radiation spread out and cool down. As the universe expands, the cosmic microwave background becomes fainter and galaxies move farther apart, driven by the increasing dominance of dark energy. In this model, as the universe approaches a state of cold, disordered emptiness, traditional notions of time lose their meaning. In this eventual cold and empty state, the universe undergoes what's called a conformal rescaling. This process involves adjusting the scale of the universe while preserving the angles between points. Penrose uses this concept to suggest that something infinitely large, like our universe's spacetime, can be mathematically transformed into something finite. This transformation allows the end of one universal cycle to seamlessly connect to the beginning of another. This cyclical model implies that the universe has neither a definitive beginning nor an end, and that the structures we observe in the cosmos are natural outcomes of this continuous process. One of the most compelling aspects of Penrose's theory is its potential for observational evidence. He suggests that certain circular patterns seen in the cosmic microwave background, known as Hawking points, could be remnants from previous cosmic cycles. Named after the physicist Stephen Hawking, these points are thought to be imprints left by black holes that existed in a past eon, which have since evaporated and left their mark on the cosmic microwave background radiation. The scientific community remains divided over the accuracy of studies that claim to have identified potential Hawking points in the cosmic microwave background data. Some researchers argue that further investigation is necessary to confirm or refute these findings, suggesting that the observed patterns might be coincidental or caused by instrumental effects. If validated, the conformal cyclic cosmology model proposed by Roger Penrose would dramatically alter our understanding of the universe. This model introduces a cyclical conception of the universe, challenging the traditional view of a singular beginning and offering new perspectives on the nature of time, cosmic evolution, and the ultimate fate of the universe. It also prompts deep questions about the role of information, causality, and entropy across epoch. Future research will likely aim to refine this model and seek more robust observational evidence. The James Webb Space Telescope is already contributing valuable data that could test predictions made by conformal cyclic cosmology. Additionally, advances in theoretical physics, such as the development of a quantum theory of gravity, may help harmonize this model with other cosmological theories. Unlike the Big Bounce theory, where the universe's expansion eventually halts and reverses into contraction before starting anew, the conformal cyclic cosmology posits a continuous expansion. This continuous expansion is fundamental to its cyclical process. Recent advancements in physics and cosmology have provided potential signs of cosmic cycles within the CMB, showing events that might have occurred in previous epochs. Moreover, the enigmatic components of our universe, namely dark energy and dark matter, continue to puzzle scientists. Some theories suggest that these elements could play crucial roles in the cycles of the universe, with dark matter potentially catalyzing the universe's eventual contraction and dark energy driving its accelerated expansion. The discovery of gravitational waves from the collisions of black holes and neutron stars has unveiled new aspects of the universe. Researchers are now exploring whether these waves can offer insights into the universe's potential cyclical patterns and assist in evaluating various cyclical cosmological models. The idea of a cosmic cycle, rooted in both modern science and ancient philosophy, profoundly influences our understanding of the universe and our place within it. If the universe operates in a continuous loop, it challenges traditional views of linear time and the uniqueness of our existence, prompting deep reflections on time itself and the broader meaning of life. Studying the cosmic cycle could also illuminate the fundamental laws that govern the universe. The ancient concept of a repeating cosmos might be crucial in solving some of the universe's mysteries. This concept suggests that the universe endlessly recreates itself, offering valuable perspectives on the nature of existence. String theory suggests that what we perceive as elementary particles might actually be strings of energy vibrating in multiple dimensions beyond our usual three. According to these theories, these extra dimensions are compactified, meaning they're curled up so tightly that even if we could access them, traveling along these dimensions would quickly bring us back to our starting point. But what if these hidden dimensions could contain entire universes? Introduced in the early 2000s, the ekpyrotic model of the universe suggests just that. According to this theory, we might live on a three-dimensional membrane that exists alongside others within a larger four-dimensional space plus time. Occasionally, our universe might collide with another, possibly housing a different universe. If such collisions occur, it would potentially explain both the beginning and the future end of our universe. In this cyclical model, the branes move towards and away from each other, colliding and then separating over and over. Each cycle from Big Bang to expansion to Big Crunch and back to Big Bang could seed the structures we observe in the universe today, such as galaxies and clusters. These structures could be the result of interactions between the branes during their slow approach before a new Big Bang occurs. While introducing concepts of additional universes and higher dimensions to explain cosmic origins might seem radical, there are compelling reasons why physicists are seriously considering these ideas. While searching, we lack concrete evidence that phenomena like the collision of universes or the broader concept of inflation actually occurred. The idea of universes colliding, as proposed in some inflationary theories, suggests that two bubble universes could impact each other, leaving detectable marks on their cosmic background radiation, similar to bruises. The theory of eternal inflation posits that while the greater cosmos continuously expands, inflation occasionally halts in localized areas. This end causes those regions to heat up and transition to standard cosmic expansion, potentially creating multiple bubble universes, each a part of a vast multiverse. Despite extensive astronomical searches, no definitive signs of these collisions have been detected. Researchers continue to explore these possibilities. Over time, another theory attempting to explain our cosmic origins has undergone revisions. Its latest versions move away from scenarios involving cosmic collisions and higher dimensions, aligning more closely with inflation theories. Now, this model suggests that the dynamics of a scalar field, a type of energy field thought to drive cosmic inflation, could be responsible for the universe's behavior, transitioning from a collapsing state into a new Big Bang without necessitating dramatic collisions between branes. The cosmic horizon marks the boundary of our observable universe and represents a firm limit on what we can see. As the universe expands, this boundary recedes ever further, carrying anything beyond it away at increasing speeds, ensuring that their light can never reach us. While we may never fully determine what exists beyond this boundary, all theories suggest that our observable universe is just a part of a far larger and possibly more complex space. This larger space might contain a multiverse with different physical laws, be part of an endlessly repeating cosmic cycle, or extend into dimensions beyond our current understanding. The truth remains elusive, and our concepts of the universe continue to evolve as we study deeper into these cosmic mysteries. We are continually piecing together clues to understand the universe's fundamental structure and its earliest moments. Through patterns observed in the cosmic microwave background, the distribution of galaxies, and experiments in gravity and particle physics, we're gaining insights that bring us closer to narrating the full story of the cosmos. We can already glimpse the fiery conditions of the universe's birth moments after its inception. With the data we're collecting, we hope to trace the universe's narrative from its fiery beginning to its eventual conclusion. Our grasp of the universe has expanded dramatically throughout human history. The beauty of science is precisely in recognizing how much we still have to learn. Today, some of the sharpest minds are exploring profound questions about the nature of the universe and what might lie beyond its boundaries. This inquiry explains more into how we define the universe. Is it everything that exists, or is it simply one part of a broader reality? Could there be other universes like our own? The possibilities are boundless, ranging from entire worlds hidden within black holes to entirely separate universes. Our innate curiosity, ability to dream, and capacity for wonder drive these explorations. We have developed numerous theories about what could exist beyond or be larger than our known universe, theories that align with existing observations, physics, and mathematics. As we look up at the stars, it's important to remember that our curiosity knows no limits. The universe, whether finite or infinite, invites us to explore, seek answers, dream, and think about. The concept of the observable universe being just a tiny fraction of a much larger cosmos opens up endless possibilities. It suggests that what we see is not all there is, that beyond our cosmic observation might be other expanses of space-time, brimming with galaxies, stars, and planets, potentially governed by laws of physics different from our own. These regions could be part of a grander multiverse, where each universe is a separate bubble floating in a higher dimensional space. The idea of multiple universes existing simultaneously challenges our perception of reality and underscores the possibility that our universe might just be one of an infinite number of universes, each with its own unique properties and histories. In these other universes, the constants and laws that could support the fabric of reality may vary dramatically. The strength of gravity, the nature of electromagnetism, the masses of elementary particles, and the behavior of dark energy could all differ, leading to universes that are wildly divergent from our own. Some might be teeming with life, while others could be inhospitable. The fundamental forces that shape their structures could give rise to complex phenomena that are unimaginable in our own universe. The theoretical frameworks that allow for these possibilities include string theory and its extensions, which posit that our universe might be one of many branes' three-dimensional objects floating in a higher dimensional space. These branes could occasionally collide, sparking the creation of new universes in a cyclic pattern of cosmic births and deaths. His cyclic model of the universe, where each cycle begins with a big bang and ends in a big crunch, only to start again, introduces a temporal dimension to the multiverse concept, suggesting an eternal sequence of universes, each emerging from the ashes of the previous. Another intriguing aspect of what might lie beyond the observable universe is the role of dark matter and dark energy, mysterious components that make up about 95% of the total mass energy content of the cosmos. In other parts of the multiverse, the composition and impact of these dark entities might be completely different, leading to universes that expand and contract according to different rhythms and patterns. As we continue to push the boundaries of technology and observation through missions like the James Webb Space Telescope and observatories like the Event Horizon Telescope, we gain more tools to know the edge of the known universe and perhaps glimpse the structures lying just beyond our perceptual reach. Each new discovery feeds into our theories and models, refining our understanding and sometimes overturning long-held beliefs about the cosmos. Moreover, the pursuit of a unified theory of quantum gravity stands as one of the most promising avenues toward understanding the true nature of the universe, including what lies beyond the observable horizon. This theory aims to reconcile the principles of quantum mechanics, which govern the subatomic world, with general relativity, the theory that describes the gravitational structure of space-time. Achieving this reconciliation might one day allow us to understand not just the small, quantum aspects of the beginning of our universe, but also the vast, unobservable regions that lie beyond. Ultimately, our journey to understand the universe is a reflection of our innate desire to explore and comprehend the unknown. It's a journey that takes us not just across the physical expanses of space, but also through the vast landscapes of human imagination and thought. As we journey into the cosmos, each discovery is a reminder of our smallness in the face of the universe's vastness and a testament to our determination to grasp the infinite. This journey, driven by our boundless curiosity, ensures that as long as we gaze up at the stars and ponder their secrets, the story of our exploration will continue to unfold, always extending towards the ever-receding horizons of our knowledge. The exploration of what lies beyond the edge of our observable universe is not just a scientific attempt, it's a philosophical and spiritual journey that challenges us to think about our place in a potentially infinite cosmic tapestry. Each theory and each observation brings us closer to understanding not just the universe, but also our relationship to it, a relationship woven through the fabric of space and time, connected by the threads of light that bind us to the farthest galaxies, calling us to explore, to understand, and to dream.